Hi everyone, in this video we're going to be learning about least squares regression. Okay, so first let's review lines, things you learned in algebra, because this is going to come up in this section. So the slope of a line, if you know 2 points that it goes through, is just the y values if you subtract them, so their difference divided by the x value difference. So y2 minus y1 divided by x2 minus x1. A lot of people know this as rise over run. The point slope form of a line is this equation, y minus y1 equals m times x minus x1, where x1 and y1 come from a point on the line, and then m is your slope. So this one is the usually the most useful form of a line to work with, because a lot of the times we know a point and then we know the slope. But another form for a line is the slope-intercept form, which is y equals mx plus b, where m is the slope and b, 0, b would be the y-intercept. And then a horizontal line is just y equals some number, and basically it's where you hit the y-axis. So you could say like the y-intercept value would be this number. And then a vertical line is x equals a number, where this number is the x-intercept. Okay, so now that we reviewed a little bit about lines, let's take a look at this example. So we have a table here for club head speed of a golf club and the distance a ball travels, and this is for 8 swings of that club. We actually looked at this example in a previous video, but based on the club head speed and then the distance the ball travels, we have corresponding points where our explanatory variable is x, in this case club head speed, and our response variable y is distance. So what we're going to do first is find a linear equation, that's going to be the equation of our line, that relates club head speed to distance. So basically that relates x to y. And we can do this by selecting any 2 points from our data, but you'll find that sometimes picking certain points is better than others. Then we'll graph the line on top of the scatter diagram, and then after that we're going to use the equation to predict the distance a golf ball will travel if the club head speed is 104 miles per hour. Okay, so step 1, let's go ahead and select x1, y1, our first point, to be 99, 258. And then we're going to go ahead and pick our second point. We can pick any of our points from our data set, but we're going to pick 105, 275. And when we pick those 2 points, it's because if we draw a line between them, it seems to give a good fit based on the scatter diagram. And good fit kind of depends on what we're looking for. In this case, we're trying to get a good line, but just that sort of represents how all of our data fits into this scatter diagram, how the explanatory variable relates to the response variable. So then let's calculate the slope. So using our 2 points, we fill them into our slope formula, and we get this, the slope is 17/6. As a decimal, we'll round it to 4 decimal places. However, just a word of caution, if you're going to compute with this, during your calculation, don't round. Use the fraction or the unrounded version. This is a rounded version. And then always just at the last step is when you round your numbers. So we're going to go ahead and use the point slope formula to find the equation of a line. We have m, we just figured out. So technically, we're going to type in the calculator 17/6 right here, or just leave the unrounded number in the calculator. It would have a bunch more 3s after it. And then x1, y1, it can come from either point, but we're going to pick our first point. So the x1 was 99, the y1 was 258, and then we just start simplifying. So remember how this works from algebra. You distribute the slope, so that's where this 280.4967 came from. And then last step, just add the 258 over. And so we have y equals 2.8333x minus 22.4967. So we have our slope and our y-intercept, because now this is in slope-intercept form. Now here's our scatter diagram along with the point through, or the line through our 2 points. And so the question asked, what happens when the golf club head speed is 104 miles per hour? And so what we're going to use is our linear equation that we just came up with, the equation of our line. So we plug in our input or explanatory variable value into our equation to get our output or response variable value. So we know that the golf ball, we predict actually that the golf ball will travel 272.2 yards if it's hit with a club head speed of 104 miles per hour based on our linear equation that we came up with. So now let's find the least squares regression line and use the line to make predictions. So basically what we want to do is we want to find the best fit line for our data. First, let me mention residual or error. So the difference between the observed value, so that's the value from our data set, and the predicted value is an error, or we call it the error or residual. Okay, so for the club head speed of 103 miles per hour, we actually had data on that. It had an actual observed value of 274 for the distance. If you plug in this number into our equation, that's where the 269.3 comes from. So how you find the residual or error is you take your observed value and subtract the predicted value. The observed value comes from your data table. The predicted value comes from plugging in things into your equation that you just came up with. So real quick, again, you plug in 103 into your equation y equals that we just came up with. That's where 269.3 came from. And so the residual or error is 4.7 yards. So we're going to look at a diagram in the next slide, but the length is represented by a vertical line, and that length is the residual or error. Okay, and it's going to be the distance between our observed point, our observed value, and our predicted value. Okay, so this is representing the residual, the difference between our actual data point and the point on our line that is being used to predict our output values. Okay, so now this least squares regression idea that we're going to talk about, basically we want to make that distance between the residual, if we go back real quick, this distance between the predicted and observed values, we want to make that as small as possible. So we're pretty much looking for the line that best fits our data so that all of the residuals between each point and our line are small as possible. And so one of the methods to do this is called the method of least squares. So the least squares regression line is the line that minimizes, so makes it small, the sum of the squared errors or residuals. Basically, how small can we get those residuals to be? That's what we're looking for. And the line that makes that happen for all of our data points, or as many as possible. So this line minimizes the sum of the squared vertical distance between the observed value and those predicted by the line. So we use this notation, we call it y hat for the predicted value, and then the observed value is just y. And so you could just, the other way to kind of sum up this statement is to say we minimize the sum of the squared residuals. So here's our least squares regression line. It's the equation of a line, and so notice this is actually in slope-intercept form. So y hat instead of just y, because y hat equals our predicted value, equals b sub 1x plus b naught. You call this b sub 0, but we tend to call this b naught. And so remember, anything right here in this form, when it's y equals something x plus something, this is the slope. Okay, so b sub 1 is our slope. And so in this case, we have a formula for how to calculate the slope for specifically our least squares regression line. So what we're looking for is this line that gives us the best fit, basically. So the slope formula for this is r times s sub y divided by s sub x. And if you recall, the s's are going to be your standard deviations. So standard deviation for the y variable divided by standard deviation for the x variable. And then if you recall from before in the past, r actually was our correlation coefficient. So b naught, this number in the back here, that's our y-intercept. And how we find that is y bar minus b sub 1 times x bar. And remember what those are your mean values. So y bar is the mean of the y variable, x bar is the mean of the x variable. And notice you want to know your slope, b sub 1, because you have to plug it into this formula to find b naught. Okay, so just a mention for what the variables are that we talked about. So let's try this. We're going to find the least squares regression line for the data that we've used in a previous example in another video. So just a little bit of data so we can do this one by hand. So in the past we've done these calculations, so if you need to refer back to that, but our linear correlation coefficient, we calculated that and we did it by hand, but you can do it with the computer. We actually used Excel in the previous video and we got negative 0.946. Our mean, that one you can do pretty quickly by hand. For x, just add up your values, divide by 5 because there's 5 observations. You can calculate your standard deviation. You can do that by hand as well or use technology to get that. That's our standard deviation for x. Your mean for y, calculate that, and then your standard deviation for y. Okay, so we have all those numbers, and so we're going to use those to figure out this least squares regression line because we actually need all these values to plug into our formulas that we just talked about. Okay, so we're going to substitute into our formula first for what we're calling the slope, which was b sub 1. And so notice we're plugging in 3 places. We plug in r, and we times that by the quotient or division of the standard deviation for y divided by the standard deviation of x. Okay, so when you calculate this, you get that your slope is negative 2.1676. And remember, if you're going to keep calculating, use the unrounded value until you're done. Now, we're going to find our y-intercept, or b naught. So we have to plug in 3 places. We just did the work to find b sub 1, so that's going to get plugged in. And then we times that by x bar, the mean for x. We also plug in for y bar. Do a little bit of our math there, and we get that the y-intercept is 18.6704. So putting that together, this is our equation of our line, but specifically our least squares regression line. So it seems like a lot of computation and a lot of values, but recognize that this is just the equation of a line. Y equals mx plus b. So we had to use our formula to find m, which we were calling b sub 1, and we had to use another formula to find our y-intercept, which we're calling b naught. Okay, and so this line would represent our data pretty well, the relationship between our variables. It would give us the smallest residuals. Okay, so the predicted value of y, which we use y hat to represent that, has 2 interpretations. One, it's an estimate of the mean value of the response variable, remember that's just y, for a particular value of the explanatory variable. Okay, so it's like the average response output variable for an input explanatory variable. And then also, 2, it is an estimate of the value of the response variable for a particular value of the explanatory variable. So the difference here is estimate of the mean and estimate of just the value. Okay, so take a look here. We're going to find from our golf club data the least squares regression line. We're going to draw the least squares regression line on the scatter diagram. We're going to predict the mean distance the golf ball will travel when we hit the club at a speed of 103 miles per hour. Then we're going to predict the distance. So notice the difference here. The mean distance and then the distance at also 103 miles per hour. And then we're going to determine the residual for the predicted value. So from our value from part C. And then answer the question, is the distance in our table, our actual observations, above average or below average among all the balls hit with a swing speed of 103 miles per hour? Okay, so let's get right into it. Okay, so we're going to do this a few ways. I'm going to show you first with a TI-84 calculator, and then next we're going to use Excel. So what I'm going to do is I want to check that my lists are clear. So actually I'm going to go to Stat and Edit. And notice one of my lists is from another example. So what I need to do first is just clear that. So I'm going to go Stat, go down to 4, which is Clear List. Then I'm going to hit Second Stat, which gives me my list, and I need to clear List 2. Okay, so now that's done. And so now I've got to go to my list. Actually, let's get there. We click Stat, Edit, and I need to put my explanatory variable in List 1 and my response variable in List 2. So let me go ahead and do that real quick. Okay, so I inputted my data. And now what I want to do is I'm going to hit Stat, and we're going to go to Calc. Actually, you know what? First, I need to turn on what's called Diagnostic On. So let me do that first. I'm going to hit Second. Way down here at 0, hit Catalog. And we're going to go to D. So I can scroll with my arrow here. Or if you look at the green background letters. Okay, so let's hit D. That way it jumps us down to where we need to be. And I'm looking for Diagnostic On. So let's just scroll a little bit. It is in alphabetical order. Go to the end here, enter, and done. Okay, so now we're ready. Let's go back to Stat. And we're going to hit right to go to Calc. And what we want is we want 4. Notice it's the linear regression, AX plus B. So we're going to hit that. And our input, our explanatory variable is list 1. So let's get our list in there. Second list 1. And our y variable was already list 2, so that's good. And then we're just going to go down to calculate and hit enter. All right, there it is. So y equals ax plus b. We use the letter m, where slope is, so the slope is the 3.1661, and our y-intercept is negative 55.7966. So that is our linear regression line for the least squares. All right, now let's do it again. This time we're going to go to Excel. So I've already typed in the data into Excel. So what I'm going to do is go up to Data, over here to our Analysis Tool Pack, so Data Analysis. And I'm going to go down to where it says Regression. Okay, so I've already typed this in, so let me clear that and show you how to get here. And we have, okay, so our input for y, that's our response variable, so that's going to be column B. Okay, we're going to take that. And then our input for x, which is our explanatory variable, is column A. And then I just want to put it somewhere on the sheet. Let's put it right there and hit OK. And it gives me a whole lot of information, but let me show you what we want is right down here. Our y-intercept for our line is negative 55.7966, and our slope is 3.1661. Okay, so here's some visuals for using the technology. This is what we figured out using the calculator, where A was a slope and B was our y-intercept. This is what you would get if you were using Minitab to do the computation. Your y-intercept would be what's called a constant, and then your slope would be the club head speed. We used Excel. We found the y-intercept and the slope. And then if you do it in StatCrunch, you're going to get almost what looks like the line equation. So distance, or y hat, equals the y-intercept plus the slope times your club head speed. So this is like y hat equals this number plus your slope times x. And so this is your equation right here for your least squares regression line. Y hat equals 3.1661x minus 55.7966. So here's our figure of our scatter diagram and our linear regression line for least squares. Okay, and you can do this in StatCrunch if you type in your data and then create the scatter diagram and the line. So notice that it's a pretty good line. It's like fairly centered among our points, and so the residual, the difference between our observed value and our predicted value, it's minimized with this least squares regression line. Okay, so we're going to use our equation, our linear equation we came up with using technology, to figure out what happens when we have x equals 103. And so we're going to use this to predict the mean distance the ball will travel when hit with the club head speed of 103 miles per hour. So we just plug that in right into our formula, and we get that the predicted distance is 270.3 yards. So we predict the mean distance the golf ball will travel when we hit it at 103 miles per hour is 270.3 yards. Then for the part D, our computation is the same thing. We plug in 103 and we're going to get 270.3 as our output. It's just the interpretation that's different. So for the mean distance, that's kind of generalizing it. It's saying any golf ball that's hit at 103 miles per hour should travel 270.3 yards, whereas the interpretation for part D, it says a particular ball hit with that speed will travel that distance. Now, from our table, the observed distance the ball traveled when it was hit at 103 miles per hour was actually 274 miles or yards, excuse me. So the residual, remember, is the distance between the observed value and our predicted value. So the residual is 3.7 yards. And because this number is positive, the observed value is actually greater than the predicted value, we can say that the distance of 274 yards is above average for a swing speed with that input of 103 miles per hour. Okay, next we're going to interpret the slope and the y-intercept of our least squares regression line. So interpretation of slope. So we know that slope is rise over run, or the change in x, y over the change in x. And so basically, if you just kind of break that down, we just know that if x, for 2/3, if x increases by 3, since it's the denominator, the y will increase by 2. And a negative slope, remember, things are decreasing. So like -4, for example, says that if x increases by 1, y decreases by 4. So just remembering what we know about slope from algebra. So in statistical models, like our least squares regression equation, we call that probabilistic. This just means that any predictions or interpretations made as a result of the model are based on some uncertainty. So when we interpret the slope of a least squares regression equation, we don't want to imply that there's 100% uncertainty behind this interpretation. So we just need to be aware that there is some uncertainty with this process. So two interpretations of the slope can be acceptable. We had a slope of 3.1661, so technically that's over the number 1. So we can say if the club head speed increases by 1 mile per hour, then the distance a golf ball travels increases by 3.1661 yards on average. And so what this interpretation means is, like, it could be a shorter distance, it could be a longer distance sometimes, but on average, this is the distance anytime we increase the speed of the club head. The other way to interpret it is saying the same numbers. If the club head speed increases by 1 mile per hour, then the golf ball will travel at a distance increase by 3.1661 yards, but that's the expected distance. So we expect that for a 1 mile per hour increase in the club head speed, the distance will increase by 3.1661 for a particular ball. So the interpretation of the y-intercept So the y-intercept for any line is the point where the graph touches or intersects the vertical axis. And the way you can find it by computing is just letting x equal 0. So for us, that's our explanatory variable. And then you solve for y, your response variable. So the y-intercept is the value of the response variable when the explanatory variable is 0. So to interpret this, we're going to ask two questions. First, is 0 a reasonable value for the explanatory variable? You want to think of the problem you're actually working on, and does it make sense? And then 2, do any observations near x equals 0 exist in your data set? If the answer to either of these questions is no, we don't interpret the y-intercept. So in the regression equation, a swing speed of 0 miles per hour doesn't make sense. And so we're not going to interpret the y-intercept, because if we're not swinging the club, then the ball's not going to travel any distance. The second condition for interpreting the y-intercept is especially important because we should not use the regression model to make predictions outside the scope of the model. What that means is we shouldn't use the regression model to make predictions for values of the explanatory variable that are much larger or much smaller than those observed. We should not use the line in the previous example to predict the distance when club head speed is 140 miles per hour, because that's actually way bigger than our highest observed speed of 105 miles per hour. So the linear relation between the distance and the club head speed actually might not continue. So we had a linear relation up until our observed data of 105 miles per hour, but we don't know what happens after that. And 140 miles per hour is too far beyond that to figure out what's going to happen. And so some dashed lines show possible relations between the club head speed and the distance the ball travels, because we don't have any observed data to work on this. So it's dangerous to use our linear regression to assume what happens too far beyond our input variables. Next, let's compute the sum of squared residuals. Okay, so we're going to compare the sum of squared residuals for the two lines that we figured out for the same data, for the club head speed and the distance the ball traveled. If you remember when we started, we found an equation, a linear equation that relates our variables. By kind of doing it by hand, we found 2 points from our data. We used those in the slope formula. We got the slope, and then we got the y-intercept. And so that's one predictor for our response variable. We can use that equation. And then we did the same thing, but we did it with our least squares regression formula. And so notice it's a different equation than our first one. Okay, different slope, and then the y-intercept's different. And then what we want to do is we want to calculate the squares of the residuals. So for each data point, and using our equation 1, I'll call it, we have the residual by just taking our original output or response variable value and subtracting our predicted response variable value. And so here's our residuals, and then this is just them squared, and here's the sum of the squares of the residuals for that equation for y hat. We're going to do the same thing for our least squares regression model, and so calculate the residual there. So just for example, we would take our observed value of 257 and subtract our predicted value of 260.8 to get our residual, and then we square that. We do that for all of our data, and then we get the sum of the residual squared. And so notice that with our first line linear equation that we came up with, this sum of the residual squared is higher or larger than our least squares model for the sum of the squares of the residual. So this is just pretty much the columns broken down from the table we just looked at, but we talked about it. And so what this is basically saying, because the least squares regression helps us find the smallest residuals, what it basically says is that no matter what other line we might come up with to model our data to fit in between our scatter points, the sum of the squared of the residuals is always going to be bigger than 49.46. This is actually the smallest number we can get out for this, some of the squares of the residuals, because this is like the best fit line for our data. All right, so we draw the graphs of the two lines obtained in the examples and their scatter diagram for the original data points. And so this just sort of helps you visualize the difference. So example 1 is the red line. Example 2 is the regression line. So we can see that they were both pretty good fit lines, but the regression line was just a little bit better. All right, that's it. Thanks for watching.